All right, so we just learned about how we can calculate the shear stress at any point within our section. Now the next part is to calculate the angle of twist within an arbitrary thin-walled section. Okay. So earlier we related the shear strain to the angle of twist using this equation for a small angle. So for an arbitrary cross section, we can relate the angle. We can say that the angle of twist would be equal to that as a function of the perimeter would be equal to the shear strain as a function of the perimeter times the length times that r perpendicular distance times s. Right. So the perpendicular radius. All right. So from the definition of shear strain, we know that phi is equal to tau over g, which again we can plug in it being here. So from that we can say that phi of s would be equal to the here, where we're just substituting tau for tau of s. So tau is now a function of s and it's no longer constant. So we can substitute in our shear. It should not be shear stress. It should be shear strain. So we plug in our shear strain into this equation here. We'll end up getting our angle of twist equation as a function of s, which is a function of our shear stress and our radius r of s at a point. Okay. So we can relate. We know that our shear flow is equal to tau of s times t of s. So we can substitute our tau of s equation here, and we can plug it in to get this equation here for theta as a function of s. All right. So for the most part, what we're interested in a lot of the time is we're more interested in getting the average angle of twist of the entire tube instead of the angle of twist at a particular point. So to determine that average angle of twist, we're going to integrate our theta of s equation over the whole area and then divide by the perimeter area. So we're going to go from 0, or the start of the perimeter, to the end of the perimeter, which would be s. Right? So if we do that, we do that integral. We're just going to plug in our value of theta s here. We're going to use that same substitution we made earlier for dA of s on the last page. So you said that dA, we're going to do the same substitution for dA of s and r theta of s. So not r theta, r perpendicular of s and dA of s. So if you look at the diagram on the last page, we had r theta of s is equal to r cosine phi, and dA is equal to these terms here. So if we plug that back in, all right, to this equation here, everything else in the equation is a constant, so we can bring it outside. So this is our dA term, and this is our perpendicular term. So what we end up getting is just an integral of d of s divided by tau of s. Not divided by the thickness as a function of s. So that's the only integral we have to across the whole. So that's the only part of the integral we actually have to do. And then we can plug in for t of for t. We can plug in. We plug in. So for q, we can plug in. We can substitute for q. We can substitute. Let me see here. So for q, we can substitute in. I think it's on the last page here. So for q, if you look at this equation here, q is equal to t over 2a bar. So we can plug that in to the next page. So you can use either of these equations to solve for your angle of twist. So in certain cases, you might know the shear flow, Q. So you would use the equation on the left. And in certain times, you might know the shear, the overall applied torsion, tau, T, capital T, and you could use that to calculate uh, the average angle of twist.